Okay, then welcome everyone to this Tewi Kolloquium. I'm happy to welcome Dr. Stefan Schauer. He is with the Austrian Institute of Technology, actually here in Klagenfurt.
Exactly.
And Stefan Schauer studied here at the University of Klagenfurt and then later did his PhD in Vienna at TU Vienna, I think. And yeah, I should also mention that he intends to submit his habilitation. So this talk is also about his habilitation project and what it will comprise, and maybe also a little bit about the timeline. So without further ado, let's start. So the title is Assessing Cascading Effects for Critical Infrastructures. It's all yours.
Thank you very much. Thank you for the kind introduction, and good afternoon, everybody. It's nice to see so many people here. I'm very happy and honored to have been invited for this Tewi Kolloquium, and for having the chance to talk a little bit about one of my core research aspects, the assessment of cascading effects, and particularly in the context of critical infrastructures. As it was just said, this is also part of my habilitation project. So this is the first talk in this context. So since maybe not everybody knows me quite well, I will just give a little bit more information on my personal background, but quite short, and then go into the motivation. So discuss a little bit why it is important to look at cascading effects and to look into this whole topic of critical infrastructure protection. And then I wanted to focus on two concepts that are at the core, if you will, of this research. On the one hand, interdependency graphs, and on the other hand, cascading effects. So they will be the main part of the talk. And then concluding, I will give a short outlook also on other aspects and other projects and results that we have already drawn. So just very brief on the highlight. And then with the next steps in the timeline, I'd like then to open the discussion also for formalities on the habilitation project and so on and so forth. In general, if there are any questions, of course, feel free to interrupt me. I think we can do this quite interactively. So my personal background, as it was just said, my roots are here with the University of Klagenfurt. So I studied computer science here before I did my PhD at the TU Vienna. At the same time, I got the offer from AIT to do the PhD there. So it was partly on the university and partly at AIT. And in that context, I was looking into quantum cryptography. So a little bit different from the critical infrastructures. But at the end of the PhD, as it usually goes, there was a little bit of lack of funding. And I was then, when I was starting at AIT, more focusing on risk assessment and security management for critical infrastructures. And I was very fortunate to be able to build up this whole topic in our center and in the group at AIT. So over the next couple of years, I was able to, through some national and international projects, build up that topic. And since 2019, I'm a senior scientist there, and since about 2.5 years, also a thematic coordinator. So I also put some logos of our past and running projects there, just to give a little bit of an overview. And of course, I'm also teaching, and from that aspect, I'm with the University of Vienna. So there, 2016, I was invited to join the newly postgraduate course ÖRISK, so which is also focusing on risk management and more also from a natural hazards approach, but also from critical infrastructures, teaching there the vulnerabilities and protection of critical infrastructures. And in the end, 2020, I did come full circle. I was also invited at the University of Klagenfurt to give the new lecture, Security Management, which I'm currently still doing together with my colleague, Christian Kolmitzer. Now a little bit overview on my research topics. As I already said, one of the major parts, or the overarching topic, is critical infrastructure protection, where I'm focusing mostly on the physical and the cyber aspects, so combining these two domains. And the research also goes then a little bit, let's say, upwards on the abstraction scale, so we're also looking at resilience on a national level and with supply chains. So there we have quite some strong connections with the ministries, BMI, the Ministry of Defense, and also Ministry of Economics in Austria. As part of that, the dependencies within and among critical infrastructures is one large part of my research, as well as the cascading effects. That's why I also chose those two topics for the focus of today. When it comes to dependencies, I'm very interested in the interplay between cyber and physical, but also when it comes to services, to processual aspects. So what goes a little bit beyond the technical, this is also some part that we are looking at. And from cascading effects, main interest focus is to look into cross-domain, cross-infrastructure. So not sticking with just purely IT, purely technical, but then also look a little bit into the OT and into other domains. And then what I would like, or what I'm also focusing on is here at that part, risk management and resilience management, so how to integrate that into these management aspects. And on the upper left, you can see also the integration to organizational processes. So here, I'm trying to set everything into the context of, let's say, current regulations like the NIS2 or the CR directive, as well as internal processes that organizations, particular critical infrastructures, are following. So the ISO 27000 family or something like that. So this just to give a very short overview on my background. So now as a motivation, I wanted to showcase a little bit what is the importance of cascading effects, where do we see that, and therefore I was taking two examples. The first one is the hacking of the Colonial Pipeline. I think this is, it has been quite prominently in the media. I don't know if here in the audience this is also something that came to attention. See some heads shaking, so no. Colonial Pipeline, this is a pipeline system on the east coast of the US. So you can see it down here. It's quite large, ranges over several states, from Houston, Texas, going up to Jersey, and also going through Atlanta, Charlotte, so some major cities. So it's one of the backbones of the gas and petrol supply in that area. And 2021, they fell victim of a ransomware attack. So it was, let's say, quite a straightforward attack. They had some vulnerabilities. So at some points, they had some VPN access, VPN for remote access. They had no two-factor authentication, so some passwords, some credentials from an inactive account were leaked. And this was the main entrance door for the attackers. So there, using those credentials and the VPN, they could get into the IT system first. And the security officers, they realized that when seeing that the billing system was affected. So, of course, as a ransomware, systems were shutting down, and some parts were not functioning anymore. What they then did as a precaution is they deliberately shut down the IT system and the OT system, so also the monitoring and control network for the pipeline. So at that point, the whole pipeline and the whole gas and petrol supply in that area was shut down. This caused, of course, a shortage, particularly, for example, in the airport of Charlotte. So there, several flights had to be delayed or even canceled because they could not refill the fuel tanks of the aircraft. The service resumed after 5 days, so it took quite a long time. And I think that's why it was, at least in America, quite popular in the media. What this shows is that with a small vulnerability, a small, let's say, open password or open credential, username, password, and with the VPN access without the two-factor authentication, this opened a door for the attackers to really do a big damage. Although, to be honest, the damage was more to the IT system because they, as a precaution, shut down the OT system. On the other hand, when we look a little bit back, 2017, there was the NotPetya ransomware, going along also with the WannaCry ransomware. So this was a phenomenon that was going all over the globe, and a lot of companies were affected. So also here it was quite a, let's say, small vulnerability or a small incident somewhere at an SME in the Ukraine where they were providing a tax preparation software that basically all the organizations that would do business in the Ukraine would have to use that. Through a malicious update, the first foothold was established, so all the organizations that were using this software, they got corrupted, and the software was also using vulnerabilities in the SMB protocol, so there they could harvest on credentials, username, passwords, and then go along the internal networks of these infiltrated companies. So there were a lot of companies that were affected. One of them, I have it here on the right, being Möller-Maersk, so this shipping and logistics company. And the problem that they had was that their entire network was infiltrated and a lot of their crucial systems shut down. What they're doing is Möller-Maersk is operating terminals, container terminals all over the world basically in major ports. And the problem that they had was that they could not access the data anymore, that they needed to know where ships or where containers should go when they come off of a ship, or which containers they should load onto a ship. So what happened is they stalled everything. For example, I have here, this was the situation at the second largest container terminal in India, and they had to shut down the whole operation there because the ships did not know which of the containers to offload and which of the containers to load. At the same time, let's say at more or less the other side of the world in New Jersey, they had a similar problem where they had a system which would scan license plates of the trucks that were entering the premises of the port. And with the system, the truck drivers, they would know where to deliver the containers, where to place them, and so on and so forth. The system in the back was shut down, so the camera could not identify the license plates anymore. The gates would not open, so there was a big traffic jam of trucks waiting to enter the premise, and this could not be handled by the people there. So what I wanted to show is that also here we have quite a small vulnerability, so this one malicious update, and with, of course, several circumstances, this spread more or less all over the world and had quite significant impact on international supply chains. So these two examples should just a little bit illustrate the problem that we have, or the challenge that we have, because this analysis of the dependencies usually is not a thing or a part of risk or resilience management processes, at least not in the past. So nowadays, the particular critical infrastructure operators, they get more aware of the situation. They know more about their dependencies, of course, because they have seen the incidents and they have also been studying the technical interplay, but there's a lot of room to improve the security for the critical infrastructures and also to optimize processes, particularly when it comes to implementing precautions, implementing security measures, and where to put the resources, where to put the money to get the best effects. The assessment of cascading effects is also the challenge here because with the complexity of the networks, it is, of course, more difficult, and particularly when it goes beyond a domain. So if it goes beyond IT and goes into OT, then usually these different domains do not talk that much. And when it goes across organizational borders, then to identify dependencies and to assess cascading effects is even more complicated. And in the end, of course, then the challenge is to build that into a joint risk and resilience management process. So usually nowadays, purely risk management is not sufficient anymore, but a lot of the organizations, they're tending more towards also resilience to get a better overview how much they can withstand, how robust they are, and how they would react under specific incidents. So just so much to the motivation, and coming now to the first part, to the interdependency graphs, I'd like to jump a little bit into detail and capture how we can describe these relations among critical infrastructures. And from the examples, we have already seen that critical infrastructures, they have developed into a highly complex and very sensitive network. On the inside, so within their technical systems, within their IT and OT networks, but also when it comes to the connection across the organizational borders. But when we look on the inside, due to, of course, digitalization and the exchange of data that we have over the last 10, 15 years, everything has been more connected. Everything is growing closer together, where IT and OT systems might have been separated in the past with remote access and all of these things. They got, of course, more connected, and of course, they also start to get smarter in that context. So we know about industrial control systems, SCADA systems, and all of these parts that are not only able to monitor, but also to control the physical parts. Here on the side, I just put some examples. If we look, for example, into a hospital, you would have very smart devices like CT scanners, or also the operation room is not classic anymore. It's not physical purely anymore, but you have a lot of cyber-physical components, thinking just of robots supporting in the operation and so on and so forth. Of course, we have very classical things like surveillance cameras, access control systems that have some kind, or let's say a rather good kind of implemented security aspects. But if we look into IoT and into sensors, then they are usually not very much, or not on the high end of a security level. So they have usually, or they provide a good attack vector or a good attack plane for adversaries to get the first foothold into networks and then start their attack from there. And of course, we have all these classical IT-related systems, starting from servers, physical and virtual, of course, desktops, workstations, and up to services, so applications that are provided by organizations. Now, this notion of interdependency graphs, it's not something very new. It's already quite established. So the first approaches have been, or are dating back to the early 2000s, when there were the first investigations on how critical sectors within an organization, within a state, for example, the organizations therein, how they are dependent on each other. There have been approaches to characterize these dependencies, so from a physical, informational, or cyber perspective, from a geographical perspective, but there are also some more vague dependencies from political parts, like guidelines or laws that are implemented and are acting on the organizations or societal dependencies, so everything that has to do with the human interaction. Now, with the time, of course, there was more research. Things were going more into detail, and there was, for example, a taxonomy built that goes into a better description of these dependencies. From an economic perspective, there were also surveys and models built up that were taking the input-output tables, so what you would usually have to describe economic exchange between states or between regions, also maybe between industrial sectors, and some input-output interoperability models were building up on that to describe dependencies among critical parts or critical areas within a state. And if you have enough data, so for example, for some particular extreme events, you could also build up Bayesian models like HCMB, so hierarchical coordinated Bayesian models that were also building on that and deriving interdependencies from that. Those were, as you can see, a little bit more specified. There were even more specialized models focusing on the interplay between the IT systems and the OT systems in the energy sector. So this combination between SCADA systems of an energy provider and the IT that is behind it, because there's also very strong connection between that. Now, right now I would like to just define or give a little bit of an overview what we, in our research, usually understand as an interdependency graph. And here, the first step, we go a little bit further than the classical approaches with including the physical aspects. So let's imagine we are in a hospital, for example. We would have very regular rooms that are located in different buildings. So we would have one building here, one building here. We would have the rooms in there really just from the physical aspect, and these rooms would be connected solely because they are close to each other. We would have other, maybe specialized rooms like the CT scanner or everything that has with the, to do with the imaging system within the hospital, or for example, operation rooms that have a higher need for security or are of more relevance to the organization. Now, taking that physical part, we can then look into the cyber-physical part where we have all these classical things like the video cameras, access control, for example. We have, of course, the physical servers, so really the 19-inch racks where the hardware is running. And to be fair, if we look at these devices that are in there, so a CT scanner could already be on the border or maybe also within, considered as a cyber-physical object. Now, they, of course, have dependencies to the rooms because they are basically located in those rooms. But, so from the direction you could see that also, for example, the access control could have an influence on the room. If the access control is not working properly, then maybe nobody can enter the room, or everybody could enter the room. So there we have already some dependencies. And here, of course, all of these devices are connected. Usually we separate between IT and OT network. If this separation is that clear or not is something of a design question and of a, how we want to use them. But in general, we could distinguish between IT and OT. And here is already another part that we are having in our model. We have different layers of abstraction. So for example, IT network would be, of course, a very complex network consisting of, I don't know, hundreds, thousands of components. That could be important, but for, let's say, the sake of the application, when talking, for example, to doctors or when talking to other people in the hospital, it could be important to abstract that complexity and put it, for example, just into one node to hide a little bit the complexity if it's helpful for the analysis. Then, of course, we have the cyber plane, so everything that is detached from the physical, although, of course, we would have some servers that are running on these machines. So here we would have the concept of the virtualization that we could bring into that. And on the cyber level, we could have an additional domain, an additional pane of the services, where we said that these are the things, the applications that are, for example, crucial for the internal aspects or for the outside aspects. So the services, they are using then some of the resources of the critical entities like a database server or an application server to provide their services to the organization. Here, for example, we have an access control. So this service here is monitoring and regulating the access control. But here, for example, we could have services that are providing services to the outside, to another critical infrastructure. So this is the understanding that we have for interdependency graphs, and this is a little bit detached from the pure technical understanding. In general, of course, it's a graph. It's just a formalized way to describe these interdependencies. We have the nodes that are the critical entities. So we will have a server rack here. We would have different virtualized database servers, and we would have two services, the access control service and maybe some video surveillance service. And the dependencies between them, so the edges between them are describing the dependencies. So a dependency from D to A means that A is depending on D2, maybe because the service is using the data that is here and only on this database. I was talking about different types of dependencies. Of course, we could then go into more detail, describe different types of dependencies, physical, cyber, maybe also distinguish a little bit in what data is exchanged. But from our experience that we had with operators of critical infrastructures, this very simplified model of combining all the different types of dependencies was convenient for them to understand the big picture. So what we are usually dealing with are people, are operators that are not very deep in the technical understanding of databases or of how a CT scanner works, but they are more on the organizational management aspect, and then want to understand from their perspective what are dependencies and what could go wrong. So this would be then the model, the way that is presented to them, and from what they could then start their work. The challenges that we have here in this context are, on the one hand, the data. So usually when we are talking with critical infrastructures, we have the problem that the data or the information about critical infrastructure is very sensitive. So here we have the problem, from a research organization perspective, to obtain that data. It does not mean that the data is not there. So there is, of course, a lot of technical data that can be found in the organization. For example, looking at CMDBs, looking at network planes, also log files from network scanners or something like this. They could be used to get a better overview on the dependencies, or at least on what systems are communicating with which other systems. On a more abstract plane, when we are talking about infrastructure, so physical infrastructure, there are some open databases like OpenStreetMap, Open Infrastructure Map, where we would have at least the highest level of abstraction to describe how network for a power operator, for a gas network or something like this could be described. The next thing is that we encountered, and that is, if you think a little bit about it, also comes quickly to mind that the knowledge about the dependencies is quite implicit. So people from one domain know about their interdependencies, but maybe these cross-domain dependencies, and this starts already with IT and OT networks, this can be difficult to identify, and we would need a lot of sector-specific knowledge to get into that, to have a realistic version or a realistic graph. And with that, of course, if we have a lot of data coming from different sources, the maintaining the data and the updating of the data is, of course, complex. So if you have different sources, internal, external, to keep everything updated, and particularly when we look at IT networks, there is so much change on a maybe even day-to-day basis that keeping up with that is a problem. So if we are starting on a little bit higher level of abstraction, we can also absorb a little bit of that complexity. So much for the concept of interdependency graphs. Any questions at the moment? If not, I'd like to go then a little bit more into detail how we can use this concept to describe cascading effects, and also then in the end to simulate and to measure them. And as first, I would like to just define a little bit what we understand as a cascading effect. So here we have the model from before with the hospital. So we have the two buildings here with 4 rooms. We have the operation room, CT scanner. And for example, now we have an incident here. We start on the bottom, on the physical part in this room. Could be, let's say, a fire breaking out in that room. Then, of course, according to the dependencies, this would affect other rooms that are close by. Of course, if nothing is done to prevent the fire. But it does not have necessarily to spread to all of these rooms. Maybe this room has a better protection, and so it's spreading here. And in this room, we have 2 workstations, so they are, of course, affected. But in the next room, let's say this is a server room, and of course, the fire has a bigger impact in that. So this would then affect the physical parts of the servers, so the racks, due to the heat, due to the smoke, but also, of course, the fire would just disrupt the infrastructure. So here we have already taken the step from the physical to the cyber-physical domain. And with the next step, of course, we are taking the step to the cyber domain, where the virtualized servers that are logically dependent on this machine to work would then also shut down. And as a consequence, the service that is relying on these servers would then also have problems or would not respond anymore. And let's assume, as we did before, that this is, for example, the application that does the access management and access control. Then with this application going down, we would have, of course, a problem with all the access control in all the buildings of the hospital. So we started with, let's say small, but a located, isolated incident here. And as a cascading effect, we might have a problem on all the buildings that are not even close to the room where the fire was breaking out. What we can take from there, and what security officers, for example, could take from there, is that maybe not only it makes more sense to protect this room, because from there a lot of technical systems in the end are depending, but if there is a fire in this building, it would make sense to have special control or special focus also on the access control of different other parts of the organization. Now, when it comes to cascading effects, also this is something that has been analyzed in the past, but the focus was more on communication networks and the maybe the connects between communication and control networks. So, for example, what we also did as a first step into that was we modeled the malware infection of a combined IT and OT network using percolation theory. So this was the approach to understand a cyber virus similar to a virus that would spread among humans, and then take that to describe the propagation of the malware through the IT and the OT system in a combined way. I was mentioning the connection between ICT and power networks, so that was a strong focus. And there also several models have been developed evolving around Markov chains and interdependent Markov models. And these models are very much specialized to this area of domain. So this is very much specialized to this connection of ICT and the power network, so the OT systems. But we found out that when we are looking at critical infrastructures, of course, they are coming from different domains, from different sectors. So we would need a more abstract model. And we would need a model that goes more into these multiple domains to describe the specialized areas of the critical infrastructures. So what we need here is that we had some models that could be applied to this very special domain of the power networks. But when we were looking, for example, also in Bayesian networks, we had the drawback that they would need very much data as an input to build up the model. And as I mentioned earlier, getting data from critical infrastructures is usually difficult. And this is why we said, okay, we want to go on a more abstract level. And also, as I said, we were starting off with this notion of infected and not infected. So this is more or less like a binary system. But of course, sooner along the lines, we realized, or it came up that we would need more operational states. We would have to do a differentiation on the effectiveness of systems to, for example, describe the availability of resources, describe the operational capacity, and so on and so forth. So we were going into the notion of a model that was more abstract to describe more different domains, more different specificities in one model. What we did is we took the concept of Mealy automata and used that as a basic concept for describing the nodes. The first thing that came in handy was, of course, the abstract states that these automata are built on. So we could use these states as representations of the operational states. And the good thing was that we could also give a certain interpretation to these abstract states depending on the domain and on the application that we wanted to look at. And the second thing is that we had well-defined transitions among these states, so we could use these transitions to describe how the system, how a critical entity would evolve when an incident takes place, and also over time, how it would change from one state to another. Next thing is that we also wanted to describe not only how one entity was affected, but we wanted to describe also what is like the output, what is the effect that goes to depending events. So we would have input events and output events, both provided by the concept of the Mealy automaton. And these output events, they could trigger another event. For example, they would then be the initiating part of so the incident for the next system. And in the end, of course, what we also said that in reality, nothing is deterministic. So we also introduced this not deterministic, the notion of probability into these transitions. So in the end, we had a probabilistic Mealy automaton to describe a critical entity. This would be a very high-level example. So we would have 4 states, S1 to S4, going from green, which would signal everything is working quite well, over to yellow, amber, to a red state, where the red state would signal, okay, something is severely damaged, broken down, or whatever. We could then treat an input state, an input symbol, a malware, for example, that would be an incident that is happening to that node. And with the transitions that I mentioned earlier, we could then describe how the critical entity is reacting to the malware. So it would change, for example, if it is in the green state, it would change from S1 to S3, so it would go into the amber state, what would not necessarily break down. If the node has already some problems, so it would be in S2, in this yellow state, then it would also go into S3, and only if it's in S3, then the malware would bring it to a complete halt. So this could be something that is coming out of discussion, for example, with critical infrastructure operators, how they would see their node to react to a malware infection. So here we have the opportunity to describe, based on the different states, how the system reacts. The other thing is that we could mix cyber incidents with physical incidents. So in the same way, we could describe how a fire is bringing a perfectly well-running system into S2, and only if there are already some problems, then it would get from S2 to S4. In this way, we can understand this also that if the fire is in one place or is acting on this node over a longer period of time, first it would get into S2, and with a longer period of time, it would then be completely damaged. So this would be one part of the interpretation, but then I said, of course, we also wanted to integrate some probabilistic aspects, so to get a little bit the reality or the experience from reality also into that, because usually when you have a malware infection, it does not necessarily succeed or bring the system down. So maybe just with a probability of 0.4, the system would go into S3, and with a probability of 0.6, it would stay in S1. The same goes if we are in a more corrupted state, or if we have a bigger problem with the functionality, then this probability could increase, so for example, from 0.4 to 0.8. Of course, if we then start to implement some measures, like a better malware protection, we could reduce the probability from 0.4 to, I don't know, 0.2, 0.1 to represent this improved system. The same also goes with the fire, and of course, beside just the input symbol, we could then also define an output symbol, which could be the same. So for example, the malware infection would be the incident, and the malware infection would also be the output. We could then also change it. For example, if nothing is happening, so if there is no state change, we could also not send any output symbol, just so that the propagation is halted at that point. But we could also think of different output symbols, for example, that here we could say it's partly damaged because it's going into S2. What we could do now with this model is we could combine it with the interdependency graph. So we have our notion of the critical entities. Then we can say, of course, for example, the S1 is the notion of fully operational, and this can be also defined for each of the nodes from the different domains separately, what fully operational means. Same as for complete breakdown, so we have an interpretation for these abstract states. And then the change of the operational states is based either on an external event, like the malware infection from the outside, or it could also be from a supplier node. So if we look a little bit more into that node, we have the same definition as before, but if we have, for example, malware as an output or fire as an output, here malware would then be sent as an input to the depending node, here A, or to all the depending nodes that we have in this system. In that way, we could then describe the propagation of the effects of an incident through the overall graph, through the complex interdependencies. And to do that, we, in the course of several projects, developed a simulation tool where you could start by defining the graph, modeling the graph with the critical entities and their dependencies. You would also describe in here the transitions. And then you could run a simulation based on an initial event, so an malware incident, for example, happening here. And based on the dependencies, you could see how the effects of that spread throughout the entire network. When the simulation is finished, you would get an overview like this here with a notion or an estimation on how severe the effects would be on the overall network. And if you, of course, run the simulation a large number of times, you would get a better distribution on how often a particular system is in a red state, what would be, on average, the overall impact, and so on and so forth. Now, the challenges that come with that are, again, obtaining the data. So here we are talking about how critical systems are evolving due to an incident. And this is something that critical infrastructure operators really don't want to share, so even less than about talking about their infrastructure. They want to talk about their vulnerabilities and what could be an effect of a malware infection. And of course, usually there's hardly any data to learn from. We had approaches in some projects to have like machine learning approach to get an overview how a particular node, like a system in the IT or in the OT level, would react to incidents. But on the one hand, we did not get the relevant data. On the other hand, maybe you don't have that many training data of a lot of malware infections and so on and so forth. The next thing is the transition probabilities. It's a core part of the model. So when we describe that, we describe the evolution of the system. And what we did in the past is to get experts, and out of the conversation with those experts, we would then get a notion of these transition probabilities. The problem here is that experts, they don't want to get pinned down on a particular number. So we had to come up with different approaches in the interviews, how to get their good feeling and their knowledge that they had also into the model. And the abstraction is important. So if you look at an IT or OT network, I already mentioned that, it's usually very complex. You have hundreds, thousands of nodes in there. Many of them might not be that important for an assessment of just the critical aspects. So the abstraction here is also an essential part to make the whole system or the whole estimation comprehensible. Now to conclude, just let's say 3 main takeaways from the last 40 minutes. First of all, that critical infrastructures and their interconnectivity is an important fact to consider and needs to get more attention within critical infrastructures, also within other organizations. Then, of course, this interdependency analysis is usually a core part or an important part of a risk assessment or a resilience assessment. but usually in practice it's not treated as that. And that we need to also build on this explicit and implicit knowledge, so that is a challenge to get that out of the people. And then, of course, the third part, that we have usually wide-ranging effects of these cascading effects that can go across organizations, across domains, across sectors, and this also has to be captured in a structured way to be prepared against incidents that could come or face the organization. From an outlook, this was, as I said, just the core part. We did several applications of this model already. So we had it in different domains. I mentioned the ICT and the SCADA network, where we combined these two networks that are placed within one network. We also then went to networks of different domains. So for example, describing a water network, describing a power network with the physical and the cyber components, and then describe how they are interacting. And here, of course, each of those nodes is then represented by this Mealy automaton model. And with that, we can then also simulate the cross-domain behavior or the cross-domain effects of an incident. We also integrated that into particular analysis systems. For example, we had a project with a port operator where they had the power, the physical and the situational awareness, and those two parts of the organization would not necessarily talk to each other, but of course you would have incidents that spread from the cyber to the physical domain and from the physical to the cyber domain. And here we were applying also our concept, extending it to what we call the hybrid situational awareness that combines the information of the two domains, and also is then able to visualize the cascading effects that grow across those domains. Similar thing we also did together with Vienna, so the municipality of Vienna, in one of our national research projects, where we built a GIS model and abstracted it as part of our approach. We were using some of the internal data and some more of the open access data, built a model, and then at that point could describe cascading effects all over the city, ranging over different domains, different systems from different critical infrastructure operators, and then could use that to do risk management and also crisis preparation in that context. And in the end, I mentioned that the combination of risk and resilience is one core part, and there we are working on a simulation-driven risk model, and also did some approach to bring that notion of combined risk and resilience into one of the standardized processes. So where we have the scenario simulation as a core part, and then have a risk and a resilience assessment part. And the goal was to fit that into something like ISO 31000 or ISO 27005 risk assessment process, so that it could also be then applied within critical infrastructures or complex organizations. That brings me to more or less the end, or let's say the contextual end. So should we do questions right now, or should I just present also the outline?
Let's do the outline.
Yeah, okay. So how to proceed from here? I have already identified several publications that we did in the past, and I think I also sent that around to some point, which are more or less over the last 5 to 6 years, the collection of the research that we did in that context. So it is coming from either conferences, book or journal contributions, and this, maybe not readable here, but I think we can share the slides in the end. This would be a first approach on how the thesis could be structured. So we would have, I would have a theoretical foundation to start with, and then focus more on the concepts and frameworks, so a little bit of the evolution, how these different approaches, how the different frameworks were developed, and also the application, so these different parts, the different domains where the concepts were applied, to give a little bit of an overview there, and yeah, finish with conclusions and outlook. And I was also requested to provide a timeline. I did a first approach. I divided it into 3 parts, each about 2 months. So the first part would be the compilation of the existing papers, so that these 16 papers that you saw earlier in that structure, to put everything together, of course. Then the second part would be to write this overarching storyline that describes the structure and the general theme, and then go into the final draft. I set a deadline at the end of the first quarter, so March 2025, to have the thesis finalized. And then, of course, it gets a little bit fuzzy, since it's, of course, my first habilitation process. So I'm not sure about the review period. I know that there's a habilitation colloquium in the end. But yeah, I'm very much open and happy for feedback and for your thoughts on that. Thank you very much.
Yeah, thank you very much. Any questions? Yes, maybe I'll take this.
I have a very specific question on one of your papers you wrote with Stefan Ras, where you say you use percolation theory with heterogeneous nodes. So these two things raised my interest, because I also worked once on percolation. Yep. So what did you do there, and how did you do it?
So the idea was to use percolation theory, so coming from this whole pandemic description of how pandemics spread. Was it the domain where you worked?
No, I worked in wireless networks.
Ah, okay, yeah. So to take that concept, and heterogeneous nodes were, because we were using nodes from IT and OT, and they were also heterogeneous in the way that they behaved. So describing this notion of infection and what the effects of that infection were, this was the core part that we described there.
But what did you analyze? Because percolation theory is often about, let's say you have a forest, and then there's also some disease, and then the question is, what's the density of the trees that you need to that the infection gets percolated, that everybody. So what in your case did you specifically analyze, and what was the result?
So first, the main thing that we analyzed was the notion of infection. So how many nodes were affected. We also looked at the differentiation between OT and IT network, so how the connection was there. And we used that to put that into a risk assessment. So to, again, with a simulation approach, get an overview on average how much the nodes, or how much parts of the network were infected, and take that as an information to maybe in a risk management where to put the measures, what would be the most affected areas, and so on and so forth.
Okay, thanks.
Okay, thank you very much for the insights. You mentioned at the beginning these economic impacts of these cascading effects. And my question would be, since you assess the severity of the incidents with the, I think, the output of the model, if you also kind of output, I don't know, a number measuring the economic impact of those incidents, so kind of loss or whatever.
Mm-hmm. So what we could do usually is to put some number on the node, so some value on the node, or more specifically on the different operational states. If they change, you could put some number on that, how much that would cost. And out of that, you could then deduce an economic impact. However, it was difficult to get that information from critical infrastructure operators. So for example, when we were discussing these things with the city of Vienna, so where we had several critical infrastructure operators in the project, and discussing with them, they would just give us a notion of, okay, this could fail and that could fail. We were asking for values on how much would it cost to repair. So this was nothing that they could give or wanted to give, let's put it that way. So this was a little bit difficult. As an outlook or to follow up on that, we are now in a project where we are looking at the post-pandemic effects, and we have a partner, IHS, which is Institut Höhere Studien in Austria. They were looking at the economic damages done by COVID, and also coming from school closures, coming from lockdowns and stuff like that. And at the moment, we are trying to combine those two aspects. So there, they have a lot of this data on a higher economic scale, so not for individual organizations, but for a region or for a nation. And this is the first part where we can really then connect that with economic values.
It would be basically based on historical data, and you wouldn't do kind of a forecast. So if you don't do anything, for example, in room 1, you'll have a loss about 1,000 for each hour that you don't do anything about it. You know what I mean?
Yeah, so this is data that we usually don't get. Yeah. So in the example before that I showed with the fire and the, we would get no specific information on what would be the loss per hour if the access control wouldn't work, or if the operation room would have to be shut down. Not because it's not there, yeah, but in the course of the project, they didn't give us. But from a conceptual perspective, we could add that value to the node and then do the calculation from that.
Thank you.
Hello, thank you for the very interesting talk. I'm actually familiar with the project, and I'm asking a question that I have been asked when I was also involved in the process, and it made me like think. So I'm posing this question again. So the question is, how do you verify the validity of the model and that you're not like overspending, since there is a lack of data and a lack of, I would say, verification, training verification set to find out whether the model is correct or not, and how do you, how did you verify the validity of the model and the fit of the model?
Mm-hmm. Yeah. So how we produce the model, and I know you know how we produce the model, but in general, we are setting up the graph and the basic parts, and then we go into discussion with the experts. They give us their notion, their estimation on the transition probability. So we work together to come down to that, and then when we do the simulation, we usually show it back to them, and we, in the discussion, do then the validation in that part. The problem is, and this is maybe something that you're pointing at, we would not have a reference. So if you have like an incident, for example, this hacking of the pipeline or the WannaCry infection or something like that, you would see the effects, and then you could usually build a model and then see if the model that you built would reflect or would get the same results. However, if the experts have experienced something like that, they also bring their bias, their knowledge, the new knowledge, into the new model when you build it, and then of course it would not completely match or not match the outputs that you would see in real life. So here we're focusing much on the exchange. Of course, we're not building a model with a group of people and showing it to them again, but we're also showing it to other people. So we have usually end users that are also verifying each other's models because they are in the same domain, for example.
Thank you very much.
Any other? Yeah.
Yeah, thank you for the talk. I didn't hear of this attack on the pipeline, and I was wondering, did they find out what was the purpose of this? Also, who was attacking this, for what reason, and might it help to know the motivation? So whether you want just to spy, enter a system, you want to break it down, something like this, to better evaluate the risk?
Yeah. So, and in that part, so for that scenario, I'm not sure whether they have investigated to the very point what was the purpose. Due to the fact that it was quite tailored to this colonial pipeline, I would not suggest that it was like normal ransomware infection which you can like buy off the black market, but it was something more dedicated or more tailored to the infrastructure. So in that way, it was, I think, an attempt to shut down the gas supply on that part, which succeeded to some degree. So it was not purely harvesting money off of the ransom, because it was also just this one company. In general, of course, the motivation would help, but usually what you would do, or what I've seen, is to distinguish 4 or 5 categories of attackers. Maybe these very script kiddies that just want to try out something, then these organized crimes, and so on and so forth. So here you could, of course, bring in that knowledge to characterize the incident, because what you can also do then is, if you have like a script kiddie, the propagation would not be that intense, or the probabilities for the propagation would not be that high, because the techniques are not that elaborated. If you're looking at a big hacker group or a state-sponsored hacker, they have more resources, they have more power. Then, of course, the infection and also the propagation, so how much of the network they could affect, that would be more intense. So you could model that using the transition probabilities, for example.
Yep.
In resilience engineering, a hot topic is the robustness against concurrent incidents. So system might be robust if an incident is happening and another incident, but if 2 occur at the same time or more, then you have often a problem. So is your model also helping to become robust against concurrent incidents, or can it be used for this type of research?
It can be used. So it is equipped with the possibility to start an incident at point 0, and then later on start a second incident that happens at another point in the network, and then you would see how they would propagate, maybe also how they would, how do you say? And verstärken? Amplify, thank you. How they would amplify each other, yeah. So you could do that.
Did you work on this so far?
No.
Not, okay.
Yeah. So we haven't had the case up until now that this was a question. So we were just focusing on one incident. We would have different instantiations, or maybe a second incident, but then really looking into the matter how they would amplify each other. Because if you have, I don't know, a fire and a malware, maybe that is not much, there's not much interaction. But if you have a malware infection and then maybe someone exploiting in the course or building on that infection, then of course you have a bigger amplification. So far, we did not really look into that.
Okay, thanks.
Thanks for the nice presentation. I have maybe a little bit out of box question, and this is risk or attacks are a adversarial 2-person game, so to speak. Now, if you have a model like yours, it also gives the attacker information where to attack most effectively. So there is a risk of risk assessment.
Yes.
How do you deal with this risk?
Yes. So we had that comment quite often when talking to critical infrastructures, Because as you just said, when we build up this graph, when we build up the simulation, we would not only give the defender, if you will, the ability to see the most vulnerable spots, but also the attacker, of course. So this would be like a handbook for attackers to do that. I don't think there is a to-the-point solution to that. One solution is that the critical infrastructures, they are not giving out their data except to trusted parties. So a research project, in my experience, was not such a trusted party that they would share their information with. But of course, they also have their cyber analysis. They have their cyber physical teams that do analysis, that also do the risk assessment, and they just try to keep that to themselves. So the only thing so far that I know is to keep the information source closed. Yeah. Yeah, sure.
This is then a roadblock for studying cascading effects, is it?
Yeah. So to speak a little bit of my past, we were struggling, well, not so much struggling to get critical infrastructures on board of projects and on board of these research questions, because they are, from their nature, they are interested in that. But when it comes to providing the data, so to really make a difference or make a huge leap, for example, they were hesitant to do that. Yeah. So this is really also a blocker for that. And to be honest, I don't have that much close ties to the inner circles of these critical infrastructures to know whether they are doing something similar in their organizations, so where they are just among themselves and with their own data in their own premises. But from what I have seen, how they are usually dealing with the risks and risk management, I'm not sure whether they are really going into that detail from a conceptual part. But it is definitely a blocker, yeah.
Okay, thanks for the talk. So first of all, if you're looking for critical infrastructures, I work for the Austrian Red Cross. We run the piece up here, so if you like, we can talk.
That would be nice.
I provide you some information. We also are affected by NIS already, so we have gone through a lot of process like there. Second question is, so far you have only mentioned incidents that affect the availability. How about incidents that affect the confidentiality or integrity of data? So, I mean, maybe the system is still running, but someone got all the medical data, for instance, in the hospital or something like that.
Yeah. So most of the requests that we had so far, they were about availability. So that's why the main parts that we did so far were dealing with availability. So these 4 states that I showed, for example, the last state was the complete breakdown and not the complete, how do you say, disclosure of information, because you could also do that. You could also say it's a complete loss of integrity with maybe some different parts. We didn't go very much into detail on that because we did not have the questions yet. But the model in itself, which interpretation you give to these states, is up to you and is up to the case of the application. So we could integrate that also into confidentiality, integrity, maybe also, and this is really something that we are currently thinking about, combining the 3. So usually you would have in ICT the CIA triad, and then maybe have not 1 aspect, but maybe have 3 aspects, and they could also interrelate with each other. But this is something that we are really currently thinking of.
Okay, thank you for the interesting talk. My question is, if you have analyzed the network, let's stay on this abstract level, can you also provide then solution how to, let's say, rearrange this network if possible, so that these accidents do not happen anymore, or are not so worst, have not so worst implications?
Yeah. So what we can do, and what we did also in the past, is we are starting from scratch, so from the situation as it is, and then of course we have the possibility to implement some security measures. Maybe we are also identifying some vulnerable point because it's red in most of the simulations. Then we can say, okay, you should focus your resources there. And we could also then add new nodes to the graph or take some nodes out of it. Play also with the transition probabilities so that we describe the state after implementing one measure. Let the system run again. So you have again this simulation. And then you see what has changed. And then you could also compare the initial run with the runs where you have 1, 2, or several measures implemented. And then by comparing those, you could also see which would be the best measures to do. So we had an approach, or we are having an approach that goes into game theory, where we play this game between the attacker and the defender. The defender has several measures at hand and a combination of those measures, and then we could bring that together with the simulation and see what would be the best measures to implement to have the highest protection of the system.
Maybe a follow-up.
Yeah.
No, it's not possible. Thank you. If you just do static analysis of this network, just on an abstract level, how much do some centralized nodes, which are connected to to many other nodes, how much do they have an effect on these worst cases?
Usually they have a large effect, but it depends on the, so let's say how well they are protected. So how we describe the transitions, how much they can be affected by an incident, so how much they change in their operational states in that case. And if you have, for example, a node that is very well protected, so there's a low probability for the state to change, then it would be still a safe spot, to be a little bit exaggerating, a safe spot, although it is several things are depending on that.
Thanks. Any more other questions? I did have one, and because I was wondering when I heard the presentation first, your model seemed like a very static model, right? Like you have dependencies between things and services and so on. Later on, it became clear to me that there is some dynamics in, the states when you have the transition of, the state one of these nodes couldn't be in. I was wondering whether you could add more dynamics to your model, because sometimes things are going on, right? Things are not just there, and you might have actions that are taken or not, and these actions might be risky themselves, right, or not. Is there anything that you're thinking along these lines, or are you happy with the model?
What we are thinking along is that right now we are going to let's say, the worst state. So we are just looking at how much a system or a network is affected. But of course, we also have the time, as you said, when things are running better. So when there are measures implemented and stuff like that. So we are currently working on bringing also this repair aspects into that. So this would be some more interaction where you could then highlight, okay, after an hour, there will be this service available again. What we don't have so far, and I don't know if it's just the technical part, is to, during the simulation, interact with the model. So usually we have an initial state, we start the simulation, and we get a result. And then we can do something with the state and then run the simulation again. But during the simulation to pinpoint and say, okay, now we have a second attack here, and we have a incident response team working on that node. We haven't done that yet.
Okay, thanks. Any more questions? Well, if not, then let's thank Dr. Schauer again, and thanks for your talk.
Thank you.